equity. We think that this kind of pattern is a very widespread thing, that it's not because of our instructors or the details of what we do, it's because of the general structures we've created in these courses. That's what we share across multiple institutions, that's what we share across multiple disciplines. A heavy reliance on high-stakes timed examinations, for example, is a key element of these classes that you just don't see in other places on campus. And there are consequences of that I think are really negative. So we've talked a little bit about measuring equity, but I said that we were interested in equity and inclusion. So how might you use data to ask or answer any questions about inclusion? I think this one is much more difficult to do, but equally important. So I want to talk about just one example of measurements of inclusion. I think that understanding the way students experience a class requires us to gather new forms of data. It's not all apparent in grades. People may perform very well and still leave. For example, we were talking earlier today about interviews of students who decided to leave a physics major, and what was found is that they were actually performing pretty well. It wasn't an obvious, like, anyone would do physics if they could. A lot of physicists have thought that for a long time. It's not actually true. So you may have to get new forms of data in order to do this. So let me just tell you about one example of this, how to get beyond performance and understand how students experience our classes. This is work that was done at the University of Pittsburgh, including by Yasemin, who's here in the second row. An exploration of student self-efficacy. So first of all, for physicists in the audience, what they've done at Pittsburgh is really neat. They've decided to instrument all their introductory physics courses by dedicating a day at the beginning and at the end of each class to measurement. Right? You want to find out what's going on. So at the beginning of the class, you give people a pretest that involves both their knowledge of physics, but also questions about affect and belonging and reasons for taking this class, right? And then you can ask a similar set of questions at the end of the class. And if you simply install that in all the introductory courses, you can start to build up evidence about what happens through your sequence and have a team of researchers do that work, right? So I think it's a really nice way of thinking about how one ought to set things up. So the title of this paper is Female Students with A's Have Similar Physics Self-Efficacy as Male Students with C's in Introductory Courses, : a cause for alarm, right? What was found in this paper is that self-efficacy, first of all, for all students in physics, falls with instruction. So students come in at the beginning of class and they think, I think I can probably do physics. By the end of the first term, they're thinking, I'm not so sure. And by the end of the second term, they're pretty sure they can't. I think there are some people who are attempting to send that message to students, but it really shouldn't be that way. I mean, you know what the students are like here at Cornell. I know what they're like at Michigan. There's nobody there who actually can't learn introductory physics. But in the course that I teach now, and the structures that we have, many of them don't. And we kind of have become comfortable giving the message that you can't. You should go do something else. All right? The paper says it this way: since the effect grows with instruction, features of instruction seem particularly important to consider, both the instructional style of the instructor and the general pedagogy used in the class. This is a kind of repeatable effect. You put it out to students, it happens over and over again. Maybe we should change what we put out to students to think about that. All right? Remember, these are female students at the end of this class getting A's in the second semester. Their self-efficacy is the same as male students who get C's. It's not the message we choose to send, but it is the message that's being received, at least there at Pittsburgh. Probably in other places too. So what are some of the lessons that we should draw from all this? First of all, the first lesson for me is that we really need to attend to difference. We need to acknowledge that the students in our class are not all the same and use data to monitor equity and explore inclusion. This is especially important in large foundational courses for a variety of reasons, but including the fact that students at that moment when they're taking introductory courses are at their most different. After all, a part of what happens as they study with us is they become disciplined. They become more the same. By the time you get them in a junior or senior level class, they've been through a lot of things together that have made them more the same. In the introductory course, they are the least the same. Their interests and goals, their background is the largest difference. This is not just true in our own classes, but it's across all of STEM education and our institutions. It's not true just for gender, but for all individuals. And I think, the idea that we need to use data in order to make sure there's equity in the world should not surprise us. Think about any other big movement for equity that you've seen in the last 20 years. Have any of them moved forward without data? Most of them have not moved forward, even with data. But it is one of the factors that starts to make people really pay attention to it. If we didn't know about pay gaps or proposal biases, we wouldn't be working on those things. And so I think this is another example of that. So that's the first thing. The second thing that I want to say about this is that we need systemic reform. This is not one class or one instructor that needs to be changed. This is our system, in a way, that needs to be changed. It's a multidisciplinary structural problem for STEM education. I think there's strong evidence that our students can learn these topics, but we create environments which favor some students and disfavor others. And it's not a problem for my class or yours, for the University of Michigan, or for Cornell, but for all of us. So here's the problem. It's a giant problem, much bigger than my class, my institution, or your institution. So how do we solve a problem that's that big? What we do when we have a problem that's too big for any one group or institution to handle is that we do together things that we can't do alone. So if we want to have generational change, we need to think about a new model for approaching this problem. We should learn from the experience that we've had solving giant scientific problems. So when I was a young scientist, I wanted to map the universe. And I would have loved to make a map of the universe by myself. I would have very much enjoyed having all that data and analyzing it and writing all those papers alone. But I couldn't. So we put together a collaboration called the Sloan Digital Sky Survey to bring people together to work together on a problem that's too big for individuals to solve. I think that's what we need to do now. We need to build a collaborative national movement to establish new norms for what these foundational STEM courses will be like. In order to make that happen, I think we need a new form of motivation. And I think this focus on equity and inclusion can be a part of that. If we can really make this educational system equitable and inclusive along with being effective, then that should provide the standard that we use. So I would like to say that even an effective course can't be excellent unless it's equitable and inclusive. And until people come to believe that's really true, that you're not doing an excellent job unless it is equitable and inclusive, and you can show that it is. So you have to attend to it too. You can't just assert that it is. You have to know that it is before you'll really know it's excellent. So this is the kind of big picture goal. How are we going about it? First of all, I want to tell you a little bit about local activities at the University of Michigan, which relate to some extent to the Active Learning Initiative that I know you have here. As we went to work on this on the Michigan campus, we decided that we really needed to reapproach the design and delivery of these classes in a collaborative way. So we launched something that's called the Foundational Course Initiative. And the Foundational Course Initiative is a program that brings together a team of people from a department to work on a class, including faculty members, lecturers, postdocs, graduate students, undergraduates, people with disciplinary expertise, together with a set of consultants for our Center for Research on Learning and Teaching. And they go to work together for a 3-year period of time on a course. The consultants from the Teaching and Learning Center get to spend a day a week for those 3 years working with the instructional team. So they can do real tasks of the development. The team gets real help from them, not just consultation. The goal is to transform 30 of these large courses, reaching about 80% of our undergraduates during the next 5 years. The provost has committed $5 million to this foundational course initiative, and the goal, stated simply, is to move away from these kind of weed-out exit courses toward a sensibility that these courses are meant to build deep roots for people. Right? The introduction to mechanics should be what? An introduction to mechanics. And people should come out of it with some knowledge of mechanics. They shouldn't come out of it with a sense that they have no place in this. I'll just mention that this initiative was a cover story article in the Chronicle of Higher Ed at the beginning of December, so if you want to read more details about how that's actually playing out. And I think a very frank article that talks about the challenges that have been associated with doing this and so on. You can check that out at the Chronicle. So that's an initiative we had been doing on our own campus. But we knew we wanted to go beyond this, that we wanted to start to partner with other institutions. And so as I tried to develop a way to do this, I thought back to my own experience in projects like the Sloan Digital Sky Survey. And there are so many ways and so many times in which scientists have come together to accomplish something together that they can't do alone. And not only the idea that we might want to do this, but actually the specific structures that we might put in place can be stolen from this way of working and applied to this new problem. And that's what we've tried to do in this project that we're launching now called SEISMIC. So let me tell you about it. SEISMIC stands for the Sloan Equity and Inclusion in STEM Introductory Courses Project. And yes, if you can come up with a good acronym, your chance of funding is somewhat higher than if you can't come up with a good acronym. I would say we loved this acronym because it talks about shifting the ground underneath introductory science courses, right? And then we recruited some California institutions, and they didn't think that was so funny. These are the institutions that are involved, a set of 10 large public research universities, about 350,000 students. So 5 from the Big Ten, Michigan, Indiana, Michigan State, Purdue, and Minnesota, 3 UC system schools, UC Santa Barbara, Irvine, and Davis, the University of Pittsburgh, and Arizona State University. One of the things that we've learned in the beginning of this process is to recognize that even though these schools share a lot, they're also quite different in a lot of really interesting ways. So when we do things together, we're going to get to see things that stretch across some of the landscape of higher ed and look at very different environments and see what those environments do to outcomes. So what are we doing in this project? We're working together for at least 3 years in a collaborative way. At the core of what we do is parallel data analysis. So we decide what we want to look at, and then we arrange to look at the same thing on all 10 of these campuses. And that thing might be some large pattern of performance differences, or it might be the specific learning in a particular class, whatever it is we decide we want to look at, focused on STEM equity and inclusion. Now that we've set up this framework, we also have created an environment that allows us to do parallel experimentation. So imagine that you're a chemistry instructor and you wanted to try out a new technique in your class. It might be a belonging intervention, for example. You could do that. You could try it out in your class, get the data, spend a year or 2 to publish it, and then it would finally come out and other people would see it, and the first thing they would say is, well, that would never work on my campus. So this question of generalizability is a big challenge for education research. So now imagine that we do that same experiment, except instead of doing it in one chemistry class, we do it in 6 different institutions that are quite different in their nature, and find out to what extent it works in multiple environments the first time through, instead of 5 or 8 years later. All right. Continuous collaboration is happening through working groups. I'll show you a bit more about that, focused on measurement, experimentation, and the structures that are needed to support reform. And then we're engaging in extended annual meetings that include faculty, staff, students, and discipline-based education researchers. I got the highest frequent flyer rating I've ever had last year because I promised I would visit all these campuses to recruit people on them, and so I did. It was like more than I did when I took my kids on campus tours. So I got to see lots of places. It was kind of cool. During the course of that, we gathered up ideas about what people were interested in doing. And these are some of the themes that came out of it. Some of the folks in our collaboration put together this portrait of all the different things that people raised, just to give you some sense of what kinds of things people on all these different campuses wanted to think about, do research on, and try and affect. So a wide range of themes. Our first annual meeting took place last summer in Ann Arbor. This is a photo of the whole group. Lots of interesting interchanges took place. We brought 4 people from each of the institutions, plus some additional members engaged in a multi-day meeting. The purpose of this meeting was to decide what we want to do. So we got all these people together. What are we going to do? We had to define scientific working groups that people wanted to come together in. And then for each of those working groups, define a list of key projects that we wanted to undertake. Really fun marketplace of ideas, people pitching different projects that they would like to try and do, things that they thought they could pursue. What came out of it was a collaboration structure that has a leadership group, including a collaboration council with a local principal investigator from each institution, setting structure and guidance for the collaboration. And then all the individual members of the institutions, all 10 of these teams, come together in 3 different working groups. And these working groups are very important for collective activity. Let me give just one example. Imagine that on each campus there are 2 or 3 people who are real data wonks, who really want to do these data measurements. Those 2 or 3 people by themselves can only do so much on their campus. But when you get those 2 or 3 people together with the 2 or 3 people from every other campus, you suddenly have a working group of 20 or 30 people. And they can divide up the work and get much more done than they could on their own. And so this working group structure has really enabled us to take on tasks together that we could never do alone. Each of these working groups has defined a set of key projects. We told them to define 4, and working group number 2 said we're better than that, so we're going to have 5, whatever. That's where it came out. Here's a list of those, and I'll put it up just for a second and maybe mention a couple. You can kind of read them. In the measurement working group, it's mostly things that have to do with using student data that already exists. So asking the basic kind of demographic questions that I already showed you some results for, extending those kinds of measures to other groups of students and other kinds of courses. In the experiments working group, there's a lot of work going on in doing classroom experiments, making changes in classrooms and seeing what happens, and doing that in coordinated ways. So one of these projects is about using back channels for in-class questions and whether that increases the probability that all students could ask questions. So some of our instructors are using technology that allows students to ask anonymous questions during class. Those questions then get filtered to a graduate student instructor, maybe shown on the screen. So there's a way for people to ask questions without needing to interrupt or raise their hands. Just another example. A lot of work going on writing to learn activities in science, which are really interesting new kinds of things. And then the structures working group is focused on how do we create the conditions that will enable this change to really take place. And I'm going to show you an example of some of the work that Marco Molinaro has been doing at UC Davis in just a second about that. The idea here is that you put together a collaboration like this, and its purpose is to enable the members of the collaboration to do the things they want to do, and to do them better together than they could alone. If we don't have that as a real opportunity, nothing will happen. The whole Sloan project is a $1 million project. That's no money. I know students may not realize this, but that's like no money for a project that's like this. We hired one person. But we have 60 people working on the project because they're all doing what they want to do, and we're making it possible for them to do it better. That's the key. So there's lots of additional projects and new working groups already being considered in thinking about this. I want to finish up by talking about data and identity a little bit. This is something that when I started this work, I was very naive about. I had never done human subjects research. I had never really thought about the social impact of the kind of research that we were doing. And we did a lot of things in the beginning that I now think were probably mistaken and certainly not thoughtful. So we're trying to use also this project to develop richer ways of thinking about how we might approach characterizing people in analyses like this in ways that would be not so harmful. I'll just give you one simple example that you maybe heard. Sometimes if you try to do an analysis of students in your class and you find that there's some group maybe with intersecting identities and there's only a few such individuals in your class, it would be very common for people with a data mindset to say, we don't have enough statistics to study them, and just leave them out. I want you to imagine what it's like to be that person who has just been told, you can't even be seen in this. Right? So there are ways to do this kind of work that can be really problematic. And I think it's important that we all are learning, even if we're physicists who come to this, we have to learn to think about how to do this more carefully. So I want to say just a few words about that. First of all, data systems regularly represent individuals with categorical labels, right? We call somebody, say they have a certain gender, or they're a first-generation student, or they're an in-state student. Any one of these things is a kind of complicated label which is kind of true and kind of not, right? They collapse a complex social identity, also usually ignoring the rest of your identity. So you become just in-state or out-of-state, nothing else, when in fact you have many other features to your identity. My colleague at Michigan, John Cheney-Lippold, wrote a book called We Are Data, about the data world we live in now, and talks about reducing people to measurable types and forgetting their real complex social identities. It's very common in equity analyses, including the ones that I've just shown you, to treat these things as unidimensional, to say the only difference between students in this class is gender, for example, when it's actually much more complicated, to use these kind of categorical approaches to identity. So as we think about it, I've been asking myself this question: how do we explore these complex intersections of identity to recognize that all of our students are actually individuals? They're actually each unique. We want to try to learn from it still, but we need to be really careful about how we do it. Now, it turns out physicists like to reinvent things themselves, to think about problems that other people have already thought about a lot. It's one of the reasons people don't like physicists. We barge into spaces and say, well, why don't you do it this way? So it turns out there's lots of people who've thought about this question before us, 30 and more years of feminist scholarship, recognizing that social identities are not separable. You can't say a person is just this or that and ignore their other identities. And they're not discrete. So the work of people like Angela Davis and Kimberly Crenshaw, who invented this idea of intersectionality theory, or at least gave it the name. I'm going to talk a little bit about this paper by Leslie McCall from 2005 about the complexity of intersectionality and how you might address it. Okay, so in that McCall paper, she talks about 3 different ways of looking at intersectionality, and I'm going to show you some examples of these. One is to recognize that the categories that exist in society, that exist in our data systems, are there because they're operational in society, they mean something. So to first at least look at those categories is a good idea. You want to be thoughtful about how you do it, but you want to at least look at that because it frames some of the relationships of inequality. A second thing you can do is to say, I have now called in my data set all these people the same. I put them in this bucket, right? They're not. So go into that bucket and pull it apart and see how they're different. So that would be intracategorical complexity. And the ideal goal of a really intersectional analysis would be to get rid of these kind of categories and recognize that they're there to produce and enforce inequalities and try to get past them. So I'm going to show you some new results from Marco Molinaro about intercategorical complexity, different groups that people might be in, and how we might begin to see the complexity that's in them. So here's an example of this. The first thing that I'm showing you is a kind of guide for what this data is going to look like. On the top is a figure that shows overall first-year GPA for a set of students. And the students are broken into 3 different groups here. There are a group of students who are not first generation and not low income. And the number of those students is shown in this figure, and the size of the block represents that, okay? That's their first-year overall GPA. Then there's a group of students that are either first generation or low-income students. They have one of those 2 traits, and they're in this circle. And the third group is a group of students who are first generation and low-income students. And in the top, you're seeing what is the overall GPA for these students. In the bottom, you're seeing what is their overall GPA in the top 10 largest courses on campus, which are almost all science and math courses. And you can see, first of all, that the GPAs are different. This is like 3.